In 1.4, we finally get to talk about functions. What is a function? What does that mean? A function has only one output for each of its inputs. So that means that every x has a unique y, and it does not have more than one possible y for its value. If any of your x values are repeated, then the data that you have does not represent a function. An example for you to compare against, we have an A and a B for two different sets of data here. The first one, in A, I have x values that are 1, 2, 5, 7, 11, and I have y values that are 3, 7, 2, 5, and 2. Now the y values are repeated, right? I have two 2's in my y column. However, the input is x, not y. So my x values, there's nothing repeated, and that means that for A, that is a function. In B, I have x values that are 1, 2, 3, 1, and 5. In this one, the value of x equals 1 is repeated. So you have an x of 1 and a y of 3, but you also have an x of 1 and a y of 1. That's not a function because the x values are repeated with different y values. So you may recall earlier that I talked about y depending on x, right? X being an independent variable and y being a dependent variable. And that means that in some way y is dependent upon x. And in the way that we wrote our linear models in the last section, y was written in terms of x. And this is possible for the A example because that is a function. Y can be written as a function of x. However, in the second one, in B, y cannot. Y is not a function of x. But if we were to flip the data, we could write x as a function of y because the x values are repeated but the y values are not. So dependence and independence can effectively be summarized by the independent variable is the one that has to have no repeats, and the dependent variable can have repeats for something to be a function, or for an equation to be a function, or for data to represent a function. Let's move on to net change. So in the last section we discussed first differences where we were just looking at the difference in y values from one data point to the next data point. In this case, net change is talking about, we're asking for the difference in our y values for a specified x values. I'm using an example. This is a table of rainfall data for years from 1995 through 2000, and the rainfall is measured in inches for that year. Now, the first difference, I would take 81 minus 90, and I would have negative 9 inches, but that's just a first difference. For net change, I would be asking a question like, what is the net change between 1995 and 1997? And so in that case, I would have to compare 1995 and 1997. For that, I take 75 inches and I subtract 90 because 75 inches was measured in 1997 and 90 inches was measured in 1995, getting me a net change of negative 15 inches of rainfall between the years of 1995 and 1997. Alternatively, I could look at 1996 compared with 1999, so then I could look at the net change between those years. So 1996 compared with 1999, and I take 62 inches minus 81 inches in order to determine the net change between those years. So negative 19 inches is the net change between 1996 and 1999. So as you can see, these measurements are very similar, but the difference being that these are not adjacent years. I'm looking at multiple years or further down in my data table than I did when I was just looking at a first difference. The first difference simply corresponds to adjacent points. The next thing to discuss is how you could determine if an equation represents a function. So we talked about it for the data tables, right? If we saw any repeated values, we can extend that same concept to ordered pairs. If you have a set of ordered pairs and the x values, or rather the first entries of those ordered pairs, is not repeated, then it is a function. If they are repeated, it's not a function. So here's an example. So in the examples that are shown here, in A, I have 1, 1, 2, 4, 3, 7, 4, 10, and 5, 13. The x values from these are 1, 2, 3, 4, and 5. None of them are repeated, so I can say that this is a function. In the second one, in B, I have 1, 1, 2, 3, 3, 5, 2, 7, and 4, 10. So my x values are 1, 2, 3, 2. Wait, 2 has been repeated. This is not a function. What about equations? So y equals x squared. Is there any point when you could plug in a value of x and get more than one value of y out of that equation? No. Any x that you plug in will be squared and will give you a specific value. It will not give you multiple values. So this is a function. And in y equals 34x cubed minus 3, again, if I plug in an x, do I get more than one thing out? No. I can plug in an x and I will always get one thing out. This is also a function. Y squared is equal to x. This is where things get a little funky, right? If I pick a value for x, so say I pick 1, if y squared is equal to 1, then y can be either plus or minus 1, which implies that if my value of 1 for x has two possible y's, which means that it's repeated. So this is not a function. Y cubed, on the other hand, if I have x is equal to 1, then y cubed equal to 1 is only going to give me 1. Because if y were negative 1 cubed would also be negative 1, so x would be negative 1. So it is a function. Y to the fourth equal to x. I have the same problem that I had with the square. X could be plus or minus 1, if x is equal to 1, then y could be plus or minus 1. And so it is not. Now, this is specific to y being a function of x. And the reason that it's not holding is because the function, the y, is being squared or raised to the fourth power. If it's raised to an even power, then it's going to have multiple solutions and it's not going to be considered a function. So this is generally the key that you would want to look for to immediately identify not a function, not a function. Usually the fastest way for most students to determine if an equation is in fact a function is to look at its graph, because it's a very visual representation of what we're talking about. And what we use for this is called the vertical line test. And so what you would do is you draw a vertical line through the graph, which I'm going to do in red. So if I draw a vertical line through the graph, does it intersect more than once. No, not in A. A is a function. If I take that line and I move it from side to side, I'm still only intersecting one point, right? The vertical line only crosses at one point as I move it back and forth. It never crosses more than once. However, if I do the same thing over here for B, what I'm going to find is that my vertical line is going to cross through 2 points on this graph. And if I move it side, like, it only has to do it once. If it only does it once, it's no longer a function. This vertical line test allows you to immediately determine whether or not what you were looking at is in fact a function. And for y squared equals x, that's not the case. It passes twice. The last topic in this section is 4 ways to represent a function. The first one is verbally, which is discussing the relations with words. Basically, you explain what the function is with words instead of with symbols or numbers. In the second being numerically, where you construct a table of values or ordered pairs, you represent the 2 variable data. That's all you have for the function representation. The third being symbolically, which is the equation, right? Everything we've done so far has been linear, so you would have a linear equation for your symbolic representation. And then the last being a graphical representation. So you draw the graph of the function. Combining these allows you to fully grasp what they mean in terms of how they're applied and how to use them. Let's take a look at an example. Let's represent the function for a day of bowling in 4 ways. If the bowling alley charges $3 for a shoe rental and $4 per game, assume that the shoe rental is mandatory and that you're not bringing your own shoes to play. So if we were to describe this verbally, you would say something like, a day of bowling costs $3 plus $4 per game, right? That is a verbal description of what the function will ultimately say. And it doesn't say exactly what was in the prompt. It's rephrasing it to show that you understand what the prompt said. Now, numerically, so second, we would construct some data based off of what this says, right? If you just rent the shoes, that's not very plausible. So I didn't do the 0-3 case, but if you're just going to play one game, that means you're going to pay $3 for shoes, $4 for the game. 3 plus 4 is 7, right? So you construct the data table. If you play another game, you add 4 to it, right? Because it's $4 per game. So 7 plus 4 is 11, and so forth, getting me to 11, 3, 15, 4, 19, and 5, 23. You can represent this as a table or as ordered pairs. I've written both here for your reference, and then I put an or in between. In this case, X corresponds to the number of games played, and Y corresponds to the dollars spent bowling. Symbolically, right, I'm going to use the same setup that I used for numerically. X is the number of games, Y is the number of dollars spent, and so Y is going to equal sum A plus BX. Now, remember, B was a rate. There's $4 per game. X is the number of games, so naturally B will be my $4, and if you're paying $3, regardless of the number of games that you play, then naturally this is going to correspond to 3 plus 4x, where your answer will be in dollars. Graphically, I can use the data table that we constructed for the numerically case. And in that case, one game, right, was $7. So I can put that about there. And 2 games was $11. 3 games was $15. 4 games cost me $19. And 5 games would cost $23. Getting me this nice linear scatter plot. To outline where that's coming from, I'm just going to draw in some little ... so you can see, right? 2 corresponded with 11, 3 corresponded directly with 15, and 4 with 19, and then 5 with 23, right? Just remembering how we put these points on the graph. Now I could connect them with a line, but it's not going to be pretty because my drawing is only so pretty, and it should intersect the y-axis right about at 3 if it's well done. And that is the end of 1.4. Thank you for sticking with me this long. See you in class.